Good morning, afternoon, or evening, everyone. My name is Nindhia with the student ID ending in 080. Today, I will be discussing about Chapter 6, which is non-ferrous metals and alloys, their production, general properties, and also application. This chapter introduces the importance of non-ferrous metals in manufacturing. Unlike ferrous alloys that are iron-based, non-ferrous metals serve in conditions where steel cannot perform, such as in aerospace, marine, or even electronic environments. They are chosen for corrosion resistance, high electrical and thermal conductivity, low density, and strength and retention at elevated temperature. Although they are more expensive, their unique properties combination make them indispensable for modern design and sustainability. Non-ferrous metals contain little or no iron, which gives them very different properties from steel. They resist rust, conduct electricity and heat very well, and often weigh less. This makes them ideal for aircraft, power lines, and chemical equipment. Here, we also see that non-ferrous metals have a wide range of specialized functions, from magnetic and optical behavior to nuclear application. Despite their higher cost per kilogram, engineers use them whenever performance requirements justify the expense. Here I have included a table of the approximate cost per unit volume for raw metals and plastic relative to the cost of carbon steel. All non-ferrous metals share several advantages. Their low density allows the designer to produce lightweight but strong structures. Most form protective oxide layers, providing natural corrosion resistance. Metals such as copper, silver, and aluminum are outstanding conductors. This is why they dominate electrical and heat transfer industries. Many are also easy to shape or machine, and their non-magnetic nature makes them ideal for instruments or marine devices. In short, although they cost more than steel, the performance gain often pays off through weight savings and longer life. Here, Table 6.2 shows the general characteristics of non-ferrous metals and alloys. This slide summarizes the main groups we'll discuss: aluminium and magnesium for lightweight structures, copper for conductivity, nickel and titanium for high temperature and corrosion-resistant surface, refractory metals for extreme heat, and several niche elements such as beryllium and zirconium. Each family solves a specific engineering problem. So material selection depends on matching these property sets with manufacturing cost and environmental conditions. Aluminium is the most used non-ferrous metals because it's light, strong, corrosion-resistant, and also recyclable. Its density is only 1/3 of steel, yet when alloyed, it achieves excellent specific strength. The naturally formed aluminum oxide or alumina film gives superior corrosion resistance, while high conductivity makes it useful in power cables and heat sinks. The Audi A8 structure shown in figure 6.2 is a good example. Every part, extrusion, casting, or sheet is aluminium, combining low mass with manufacturability and energy efficiency. Aluminium is produced in two main steps. First, the Bayer process, which extracts alumina from bauxite using sodium hydroxide. Second, the Hall-Harlip process reduces alumina electrolytically in molten critolite at nearly 950 Celsius. The reaction deposits pure molten aluminium at the cathode while oxygen reacts with the carbon anode to form carbon monoxide and carbon dioxide. Because this process consumes about 15 kWh per kilogram, recycling aluminium is vital. It saves around 95% of that energy. These methods explain why aluminium plants are often located near inexpensive hydroelectric power. Aluminium alloys are identified by a 4-digit number where the first digit denotes the main alloying element: Cu for copper, Mn manganese, Mg magnesium, Se silicon, and Zn as zinc. For this example, we are going to use the letter X for the last 3 digits of the alloying elements. So, for example, 2XXX series, aluminium and copper, are high-strength aircraft alloys, while 5XXX aluminium, and magnesium, they resist seawater corrosion. Tempered designation shows how the alloy was processed. H for strain hardened, T for heat treated. A familiar example is 6061 T6, a heat treated aluminium, magnesium, and silicone alloy offering an excellent balance of strength and workability. Knowing these designations help engineers select suitable materials for forming or welding. Table 6.4 shows manufacturing characteristics and typical application of selected growth aluminium alloys. Aluminium alloys such as 6061 or 6063 or 6061 and 6063 exhibit yield strength from 180 to 300 MPa with an elastic modulus near 70 GPa. When we divide strength by density, we get a high specific strength. One reason aircrafts use aluminum skin instead of steel. Thermal conductivity is also high, so aluminum efficiently transfers heat. The downside is its relatively low melting temperature, limiting service above 300 Celsius. Because it's non-magnetic and easily shaped, aluminum remains the go-to material for transport and electrical industries. Manufacturing processes for aluminum are diverse. There's rolling, extrusion, forging, and die casting. It welds well using TIG or MIG or friction stir techniques. Through oxide removal and precise control are required. Adhesive bonding and riveting are also common in aircraft structures. Heat treatments like solution aging increases strength through precipitation of fine intermetallics. Anodizing improves corrosion resistance by thickening the protective oxide layer. Altogether, aluminum offers a near-perfect mix of strength, corrosion resistance, and manufacturability. Here, we see how different alloys match specific application. Alloy 2024T3 is used for aircraft skins due to its strength and fatigue resistance. 7075 TG for highly stressed wing sections. 6061 TG for automatic frames. 5083 H321 for marine structures. And 3003 for cans and foils. Note that recycling aluminum saves almost all production energy, reinforcing its environmental value. Engineers must balance strength, corrosion, resistance, and formability when selecting an alloy for each product. Magnesium is the lightest structural metal, about 2/3 of the density of aluminum. It offers good damping and decent strength, making it perfect for lightweight components in cars, aircraft, and handheld tools. However, magnesium oxides easily, so coatings or anodizing are required. Its low density provides significant weight savings, but designer must consider its flammability and moderate corrosion resistance. Typical use includes steering wheels, camera housing, and gearbox castings. There are two major production methods: electrolytic extraction from seawater and thermal reduction, the pigeon process, using dolomite and ferrosilicon. Magnesium alloys cast easily, making die casting their most common manufacturing process. Machining requires sharp tools and coolant to avoid ignition of chips. Because welding is difficult, mechanical fastening and adhesive are preferred. Surface protection is essential to prevent rapid corrosion, especially in saltwater environments. Next, we are moving on to copper, its properties and applications. Copper is prized for its outstanding electrical and thermal conductivity. Second only to silver, but much cheaper. It also resists corrosions and is easily shaped. Because of these features, copper dominates in electrical wiring, transformers, and heat exchangers. Its ductile allows it to be drawn into thin wires or rolled into sheets without losing conductivity. The reddish color and malleability also make copper valuable for roofing, coins, and decorative elements. Adding zinc to copper forms brass, which increases strength and machinability while maintaining corrosion resistance. Perfect for cartridges and instrument fitting. Adding tin, aluminum, or silicone creates bronze, which offers superior wear resistance and strength. For instance, tin bronze is used in bearings, while aluminum bronze serves in marine propellers. Each alloy alters colors, hardness, and corrosion behavior, allowing engineers to tailor properties precisely for the operating environment. Nickel is a tough, corrosion-resistant metal used both alone as an alloying element. It resists oxidation and maintains strength at elevated temperature, which is why nickel is found in stainless steels and plating. Its magnetic properties at room temperature makes it useful in sensors and magnetic materials. The combination of strength, corrosion resistance, and heat stability justifies nickel's higher cost in chemical, marine, and aerospace industries. Next, here in Table 6.8, you can see the properties and typical applications of selected nickel alloys. Nickel forms the backbone of many high-temperature superalloys. Examples include Inconel 700F18 for turbine disc, Monel, which is nickel copper for marine use, and Hastelloy, which is a formation of nickel, molybdenum, and Cr for chemical resistance. Nickel alloys are challenging to machine and require robust cutting tools, but offer superior performance at extreme conditions. Their resistance to creep and oxidation makes them ideal for jet engines and power turbines, where the temperature could exceed up to 1000 Celsius. So, what are superalloys? Superalloys are engineered to maintain mechanical integrity under high stress and temperature. They derive strength from solid solution and precipitating hardening, especially the Y-phase. The Y-phase, or the FCC structure, face-centered cubic structure of titanium aluminum, and form careful grain boundary control. They're divided into nickel, cobalt, and iron-based systems. Nickel-based superalloys dominate due to their balance of strength and corrosion resistance. These alloys are crucial wherever performance and reliability outweigh cost. Now moving on to their performance and applications, superalloys operate continuously up to 1100 Celsius. They form turbine blades, disc, and combustion parts in jet engines, and are also used in nuclear and chemical plants. Processing such materials require vacuum casting and precise heat treatment. Because they harden quickly, machining is difficult. Coatings like ceramic thermal barriers are applied to manage heat and oxidation. Their development represents one of the most advanced achievements in metallurgical engineering. Here are the properties and typical applications of selected nickel-based superalloys at 870 Celsius or 1600 Fahrenheit. For example, the alloy astrology, their typical application is forging for high-temperature use. Now, we are moving on to titanium, their properties and importance. Titanium combines high specific strength with exceptional corrosion resistance. It's roughly 45% lighter than steel, yet equally strong. The titanium dioxide film gives stability even in seawater and strong acids. Titanium's biocompatibility makes it ideal for implants, while its non-magnetic nature suits medical imaging. In aerospace, titanium reduces weight while tolerating high stress and temperature, which is crucial for jet engine compressors and also airframes. Titanium is produced by the Kroll process, where the TiCl4 or titanium tetrachloride is reduced with magnesium to form a porous sponge later melted into ingots. Alloying controls crystal structure. Alpha alloys are weldable but moderate in strength, where beta alloys can be heat treated for higher strength. The alpha alloys plus beta alloys, such as the grade 5 titanium alloy or Ti6Al4b, balances both. Processing requires vacuum or inert atmosphere to prevent contaminations. Despite high cost, titanium's performance justify its use in demanding environments. Refractory metals, tungsten, molybdenum, niobium, and tantalum, have the highest melting points of any metals, exceeding at 2,400 Celsius. Their strength and stability at extreme heat makes them ideal for rocket nozzles, furnaces, and electrical contacts. However, they are dense, difficult to machine, and expensive. Engineers must weigh these trade-offs when designing components exposed to intense thermal loads. Because of their high melting points, refractory metals are processed by powder metallurgy, vacuum arc melting, or electron beam melting. They oxide rapidly above 600 Celsius, so protective coatings are required. Although forming and joining are limited, their ability to retain strength where other metals soften makes them irreplaceable in specialized aerospace and energy systems. Gold, silver, and platinum are known for their rarity and excellent corrosion resistance. Beyond jewelry, they play crucial industrial roles. Gold and silver serve in electrical contacts for reliable conductivity, while platinum and palladium act as catalysts in chemical and automotive applications. Despite their high price, the unique combination of conductivity, ductility, and resistance to tarnish justifies their use in precision instruments and electronics. Zirconium resists corrosion and allows neutrons to pass freely, making it perfect for nuclear reactor cladding. Hafnium, its twin element, absorbs neutrons and is used for control rods. Beryllium is extremely light yet stiff, used in aerospace optics and X-ray windows, but it's toxic when inhaled, so strict safety measures are mandatory. These specialty metals illustrate how narrow chemical and physical advantages can create entire industries around a single element. Shape memory alloys, especially nithiol and ETI, can deform at low temperature and then recover their original shape when heated. This remarkable behavior arises from reversible transformation between martensitic and austenitic crystal structures. Shape memory alloys combine high elasticity, biocompatibility, and functional response, leading to their use in self-expanding stents, actuators, and temperature-sensitive couplings. Transformation temperatures, defined when martensite or austenite exist. By adjusting compositions, engineers tune these points for specific environments. SMA or shape memory alloys store and release large amount of strain energy, but repeated cycling can cause fatigue. Their cost and limited strain range restricts use to specialized systems like robotics, medical devices, and aerospace actuators. Amorphous or metallic glass alloys lack crystalline order, created by rapid cooling that prevents atoms from arranging into a lattice. This structure gives extremely high strength and hardness, excellent wear and corrosion resistance, and soft magnetic properties. However, the absence of dislocation also makes them brittle. Understanding this atomic structure helps explain why metallic glasses perform so differently from conventional alloys. Amorphous alloys are produced by melt spinning, sputtering, or thin section casting methods that achieve cooling rates over 10 raised by the power of 6 Celsius per second. Because only thin ribbons or small parts can be quenched fast enough, component size is limited. Their unique magnetic efficiency leads to use in transformer cores, while high hardens to wear resistance coating and precious springs. Despite manufacturing limits, research continued to sculpt up bulk metallic glasses. Metal foams are lightweight structures composed of interconnected pores. They combine the stiffness of metal with the low density of foam, resulting in excellent energy absorption. Aluminium foams are the most common used for crash protection, vibration damping, and also acoustic insulation. Their open cell structure also allows vacuum gripping and also filtration applications. They represent an emerging class of engineered lightweight materials. Foams can be produced by adding foaming agents to powders or molten metals, Foams can be produced by adding foaming agents to powders or molten metals, or by casting around space-holding particles later removed. Density can be controlled between 20% to 60% of the solid metal, allowing designers to tailor strength and weight. Although still costly, foams are increasingly used in electric vehicles and robotics because they absorb crash energy effectively while remaining recyclable. Now, let's move on to the summary of nonferrous metals. This summary compares the main families. Aluminium and magnesium offer low density for transport. Copper gives conductivity. Nickel and titanium provides high temperature and corrosion resistance. Refractory metals withstand extreme heat, and precious or specialty metals supply unique chemical function. The choice among them depends on balancing mechanical properties, environmental resistance, manufacturability, and cost, a central principle in material engineering. And now we are going to recall key formulas engineers use when evaluating materials. So first, we're going to start off with the key formula for specific strength, specific strength. The key formula for that is sigma per rho, which compares strength per weight. Aluminium's value explains its aerospace dominance. Moving on, specific modulus, or E per rho. It measures stiffness per weight, crucial in vibration-sensitive designs. Next, we have electrical conductivity, which sigma equals to 1 per PE, relates resistivity and current flow for conductor selection. Understanding and applying these ratios allows us to quantitatively compare materials beyond simple tensile tests and choose the most efficient metal for each design problem. Now, that is the end of the slide. As a conclusion, nonferrous metals and their alloys form the backbone of advanced engineering. From lightweight aircraft structures to high-temperature turbines and precise electronic components. Understanding their properties and processing routes allows mechanical engineers to design more efficiently, durable, and sustainable, and is also sustainable for the system. To conclude, Chapter 6 shows us how nonferrous metals extend the boundaries of engineering performance. Each family, aluminium, magnesium, copper, nickel, titanium, and many others, serves a precise purpose in modern technology. As mechanical engineers, our responsibility is not only to understand their mechanical and physical properties, but also to evaluate cost, recyclability, and manufacturability. By mastering this knowledge, we can design components that are lighter, stronger, and more efficient while minimizing energy use and material waste. In the end, the study of nonferrous metals is not just about chemistry or metallurgy. It is about innovation and sustainability in engineering practice. Thank you so much. Thank you very, very much for your attention and your time. I would also like to apologize if there are any mistakes or inaccuracy in my explanation. All the information presented here is based directly on the textbook Manufacturing, Engineering, and Technology by Kalpakjian and Skimmit. Once again, thank you so much for listening. That is all that I have to offer, and bye-bye.